Alright people, I'm not going to lie here. These notes are long. There's like 7 questions in these notes. I will try to get through it as fast as possible, but hang in there. These are the longest of the unit, and hopefully you survive. If I see you tomorrow in class, you have survived these notes, and congratulations. Alright, let's get started. Alright, so like the title implies, we're going to be talking about elements, compounds, substances, and mixtures. Fortunately for you guys, even though these notes will be long, fortunately, you should know pretty much all of this. This should be review for you. You probably should have gotten it in at least 8th grade, if not earlier. So let's get started with our first question. What is an element? So, what is an element? An element is the simplest form of matter, okay, which means that an element cannot be broken down into anything different, okay? So it's the purest, simplest form of matter. In fact, elements are going to be the building blocks of all the rest of the matter, the entire universe. All right, so in addition to being the building block of all other kind of matter, elements can either exist on their own as themselves, like pure gold, pure silver, okay? Or they can exist in combinations with other elements, okay? So, for example, we saw that copper and zinc, when we mix them together, okay, make brass. Or, carbon and oxygen can form carbon dioxide, okay? Hydrogen and oxygen can, come together and form water, H2O. So, elements can exist either on their own or in combination with other elements. All right, and the last thing we're going to talk about elements is how many elements there are. Okay, and as of right now, there are about 112 known elements, okay? And others are, man-made by, protons being bombarded into the nucleus of other atoms, making bigger and bigger atoms or elements. So we'll talk about that later. But for right now, about 112 known elements exist in, in the world. Okay, so enough about elements. Let's take a look at what a chemical symbol is. Okay, because we're going to use these when we're talking about elements. All right, so question number 2, what is a chemical symbol? A chemical symbol is, a symbol that stands for an element's name. So if we see here on the periodic table, which we're going to be taking a look at and discussing next week, is you're going to find all of the elements possible, all 112 known elements arranged in this periodic table. And what you'll see is you'll see a name, calcium, for example, and then you'll see a symbol, okay? It's either going to be 1 or 2 letters, okay? So for calcium, it's Ca. That's the element symbol. So instead of writing out calcium all the time, calcium hydroxide, or calcium iodide, or whatever, all we need to write is capital C, lowercase a, bam, that stands for calcium. Okay, so that's what a chemical symbol is. So let's discuss a little bit more about how these chemical symbols work. So like we said, it's either going to be 1 or 2 letters, and the first letter is always capitalized. So if there's just one letter, like for example, here we see on the right here is potassium. There's one letter, it's capital K, okay? If there are 2 letters, the first one is, again, always capital, and that's, basically going to tell you that it's a new element that we're talking about, okay? So, and then the second letter is always lowercase. So if it has a second letter, it will be lowercase. If it doesn't have a second letter, then it doesn't matter. So basically, one of the tricks, if you're taking a look at a chemical formula, which is basically a bunch of chemical symbols together telling you what kind of compound it is, if you count up the number of capital letters you see in the formula, that's how many different elements you have in that compound. And we're going to take a look at that in our next example here. But let's just give a couple more examples to write in our notes about what a chemical symbol is. All right, so to add to our list, another example, copper. Its symbol is Cu, capital C, little u. So anytime you're writing out the word copper, don't just write the symbol, capital C, little u. Okay, is copper. Same thing with oxygen. Oxygen is just capital O. Okay, so that's the symbol for oxygen. So anytime you see capital O anywhere in chemistry, it means oxygen. All right, now let's take a look at when we combine elements together, we make what's called a compound. So let's take a look at compounds. All right, so our third question, what is a compound? A compound is a combination of two or more different elements, okay? They have to be different elements combining together to make a compound. For example, if you take a look at your elementary knowledge page, okay, you see what's called diatomic gases, like oxygen, which is O2, and chlorine, which is Cl2, okay? Those are not compounds, all right? Those are elements that are always found as basically Siamese twins. Okay, so because they're not different elements, we can't call them a compound. Okay, so I'll show you an example of a compound in just a minute, but just know that they have to be different elements coming together to make a true compound. All right, let's take a look at some of the features. All right, so one feature about compounds is that they are going to have very different properties than the elements that make them up. Okay, so elements have their own properties, and when you combine them, they make something completely different. That's why we call them chemical changes, okay, because we're changing the chemical composition and we're changing all of the properties about it as well. Okay, a really good example is table salt, okay, which is sodium chloride. Let me show you what the constituents look like, and then what sodium chloride actually looks like. All right, so we see here, sodium is actually a metal, okay? Pure sodium is a shiny, silver-looking metal, okay, that you see right here. And chlorine is, on the right-hand side of our periodic table, it is a gas, okay? And so you can see here, it's kind of looks like a greenish, yucky gas. All right, so when we mix a silver metal called sodium and a greenish-looking gas called chlorine, okay, we get sodium chloride, which, NaCl, okay, which is white crystals. Okay, who'da thunk, right? So we see here that the elements that make up the compound have completely different properties, okay? Sodium by itself, you ingest it and stuff like that, is toxic. Chlorine by itself, inhalation, toxic. Put those two together, react those two together to make a compound, your body needs it, okay, to function. Sodium chloride, we sprinkle it on our French fries, all right, and our body uses it for, brain function, for kidney function, for every, cellular function, we need sodium chloride. So it's kind of cool that compounds have different properties than the elements that make them up. All right. So one last thing about compounds is we're going to talk about those chemical formulas that I showed you earlier. So let's take a look at what a chemical formula is. All right. So just how, like we saw with elements, how they are represented by chemical symbols, compounds are represented by what we call chemical formulas. Okay. So a classic example, one of them that we just talked about here is sodium chloride. Okay, that is a chemical formula for sodium and chloride. Okay, so instead of writing out sodium chloride the whole time, you can just write NaCl, sodium chloride. All right, another example is water. Water's chemical formula is H2O. Okay, so it tells us, all right, that water is made from 2 hydrogen atoms. Okay, so 2 hydrogens. Let's get that Y in there. 2 hydrogens and 1 oxygen atom. Okay, so when we combine hydrogen, which is a gas, and oxygen, which is a gas, okay, we get a liquid called water. And so again, this little symbol here, okay, this 2, is what we call a subscript. Okay, we're going to get into more of that a little later in chemistry. But subscripts tell us the number of atoms in the compound. So they tell the number of atoms in our compound. So in our compound of water, we have 2 hydrogens and 1 oxygen. Okay, if there is no subscript, like oxygen has nothing behind it, okay, it's always assumed to be 1. All right, but we don't ever write the ones there. It's like in math, right? You could have 3 or x minus 3. You don't need to put 1x minus 3, right? The 1 is invisible. Same kind of thing with chemistry. Okay, 1s are usually invisible. So in this case, with 2 hydrogens, we have to write the 2, but the 1 oxygen we just write O, and it's it is believed to be just 1. Okay, all right. So that's it about compounds. Let's move on to substances versus mixtures. Our 4th question is, what is the difference between a pure substance and a mixture? Okay, so it should kind of be common sense, right? That a pure substance is pure. There's, unchanging, constant chemical composition, versus a mixture where we've got, 2 different types of chemicals or compounds together. Okay, so let's just kind of break it down a little bit and take a look at the difference. All right, so a pure substance is matter that has uniform and unchanging chemical composition. All right, classic example of a pure substance is pure water. Pure water is always made of 2 hydrogens, 2 H's, and 1 oxygen, right, to make H2O, the chemical formula for water. Okay, so pure water always is made of H2O. Okay, no matter if you take it from, the lake in Tahoe or, the Indian Ocean, okay, the pure water substance is going to be H2O. Now, however, as soon as you add something to the water, it's not a pure substance anymore. So, if we add salt to water and make seawater is not a pure substance. All right, so let's talk about that. Okay, so salt water again is not a pure substance. Okay, because there'll be different amounts of salt depending on where you get your salt water from. Okay, if you mix your own, you can put a tablespoon of salt water into a cup of water, or you could put a cup of salt into water. Okay, you're going to have a different amount of salt. Same thing with the oceans. Okay, some oceans are saltier than others. Okay, and different parts of the oceans are saltier than other parts. So because it's not a uniform and unchanging chemical composition, okay, meaning that it's not uniform, it's always changing, it's not a pure substance. Okay, so if it's not a pure substance, it's what we call a mixture. Okay, so let's take a look at the definition of a mixture. All right, so a mixture again is a combination of 2 or more pure substances. So in our salt water example that we had right here, okay, we said it's not a pure substance, okay, because it has both water and salt in it. Okay, so it must be a mixture. All right. Now, mixtures are going to have physical properties that depend on their composition. So the physical properties of mixtures will depend on what they're made of. Okay, so it's just simple as that. It's going to be different for every mixture there is. What kind of melting point, freezing point, salinity, solubility, all of that stuff is just going to depend on what it's made of. So just a few examples of some simple mixtures. Sand and water is a mixture. Okay, salt and water is a mixture. You combine any two substances together, you're going to get a mixture. Okay, so that's that's that basically. Okay, now let's take a look at what kinds of mixtures we can have, because there are 3 different kinds of mixtures that are possible. All right, so our 5th question is going to take a look at what kinds of mixtures we can have. So, for example, the salt and water mixture, okay, versus a sand and water mixture, 2 very different mixtures. Because if you've ever noticed, if you put salt and water together, it dissolves and you get kind of this clear liquid. However, if you put sand and water together, does sand dissolve in water? The answer is no. Okay, otherwise we wouldn't have beaches. So that's a different kind of mixture. So let's take a look at these 2 different kinds of mixtures. The first type of mixture that we were talking about, salt and water, is what we call a homogeneous mixture, okay, or homogeneous mixture. You can say it either way. Basically, it's a mixture that when you mix the 2 substances together, they dissolve in each other and they look uniform. Or they completely mix, okay, to have like the same look all the way through, okay. Basically, it looks like it's dissolved in the other one. So, for example, salt dissolves in water, so it's a mixture of salt and water. Homogeneous mixtures are also what we call solutions. So that is another word for solution. Okay, so homogeneous mixtures are also known as solutions. All right, so let's take a look at the other kind of mixture, the sand and water type of mixture, and that's what we call heterogeneous. A heterogeneous mixture is one that does not blend smoothly. Okay, so basically what you can see is the individual substances that make it up. So if you took sand and water, okay, and you put it in a cup, you would see the sand layer on the bottom and the water layer on top. It's a heterogeneous mixture. They're both in the same container, but you can see the parts and they're not, fully blending smoothly or dissolving in each other. Okay, so that's what we call a heterogeneous mixture. If you can see the parts that make it up, it's a heterogeneous mixture. Okay, now the third type of mixture we're going to talk about is a mixture of metals. And if you have, aluminum alloy wheels or something like that, or if you play, a brass trumpet or, tuba or whatever in band, you are working with a type of mixture called an alloy. So an alloy is a mixture of either 2 metals together, okay, like we did with our pennies. We mixed, the copper and the zinc, and we made brass, okay, or with a metal and a non-metal. As long as there is a metal in it somewhere, it's an alloy, okay? So let's take a look at a few examples. So steel, okay, is, common thing that construction, sites use to build the, skeletons of buildings, and even, the hard metal of your desks are probably made of steel. Lots of items are reinforced with steel, and steel is not an element on the periodic table, but it's a mixture or a combination. It's a compound. All right, it's made of iron, okay, which is a metal on the periodic table, and carbon, all right, which is a non-metal on the periodic table. So if you mix the metal iron and the non-metal carbon, you make a stronger metal called steel. Okay, and then again, our pennies that we made on the first day of school were brass. They weren't gold, they were brass. And again, brass is zinc and copper mixed together. Okay, because both of these examples have metals in it, it's called an alloy. All right. So let me just kind of show you examples of each of these 3 types of mixtures, and then we'll move on to our last 2 questions. All right, so here are some pictures to kind of just help you remember the difference between the homogeneous and heterogeneous in alloy. So homogeneous is kind of like Kool-Aid. Everybody loves Kool-Aid, right? You mix the water and the sugar Kool-Aid packet together, and you get a delicious drink, okay? But you can't see the parts. You can't see the water, and there's no water layer and sugar layer. It's all mixed together, so that's homogeneous. Now, heterogeneous is like this little bean mixture here, okay, where you can see the individual little grains of rice and the little kidney beans and navy beans, and look, there's black-eyed peas in there. Okay, let's get it started in here. Anyways, so that's a heterogeneous mixture where you can actually see the parts. And then our last example here of alloy, you can think of, pimped out rims on your car. A lot of, jazzy rims are made of aluminum alloy. Well, aluminum is a really lightweight metal, okay, which is good if you want to go fast in a car. But it usually means that it's also very malleable or easily to bend. Well, if you mix aluminum with a heavier metal, you get a stronger aluminum alloy, okay, which is what a lot of car manufacturers and rim manufacturers use, is aluminum alloy in not only in the wheels but also in other car parts as well. It makes it stronger, and B, it makes it able to withstand higher temperatures, okay, if we're talking about engine parts and stuff. Anyway, so that's our 3 kinds of mixtures. All right, we are almost done. We've got 2 questions left. The next question we're going to talk about is what's called percent composition. All right, our 6th question, what is percent composition? We actually worked with percent composition in our previous lab that we did last week, with the mixtures and the separating the mixtures with the magnets and stuff like that. We're kind of working with percent composition. Basically, it's a way to express the amount of each substance in a mixture. Usually we do it with mass, okay? So we're going to take, the mass of one substance, okay? And then we're going to take the mass of the entire mixture that substance is in, and we're going to figure out, how much mass is our part compared to. All right, so like I said, it's typically calculated with mass, but you could take, volume as well. But we're going to deal mostly with mass and percent composition. So if we have a mixture, okay, we're going to measure the mass of the total mixture here, okay, and then we're going to separate that mixture out into the different substances and measure those substances' mass. Well, if you're talking about a specific substance, okay, you're going to take the mass of the one substance, divide it by the mass of the total mixture, and then times that by 100 to get a percent, okay, and that's what we call percent composition. All right, so you could do that with anything basically. You could even find, in a sample of H2O, you could even find, the percent composition of hydrogen, okay, versus the oxygen, okay. You just weigh out the hydrogen divided by the total mass of the water, and then that's your percent composition of hydrogen. So that's how we're going to do that. And you'll have some practice problems next class as well to kind of help you work through that. Now we are on to our very last question of these notes. You've come to the end. You have survived. And it's super easy because it's something you've definitely seen before. So let's take a look. All right, our last question for these notes. What do the letters in parentheses tell you in a chemical formula? So typically, when you're given a chemical formula, all right, like NaCl, okay, you'll be given a little symbol behind it, okay, whether it's S or AQ. Okay, that little symbol is very important because it tells you the state of matter that particular compound or element is in. All right, so it tells you the state of matter. So, for example, G, okay, if there's a little g behind it, it would mean that it's a gas, okay? S, like here, okay? S means that it's solid. So, for example, in this situation here, NaCl with a little S behind it means that it's solid sodium chloride. It's, like what you would fight in your salt shakers. Okay, an L, okay, usually it's kind of, if you're writing it out, you're going to put it in like a little cursive L. That way it just doesn't look like a 1, okay? So usually when we write it out, we do a cursive L. That means pure liquid, okay, which is super, super, super different than AQ, which is aqueous. All right, AQ or aqueous means dissolved in water. All right, so it's different than being a pure liquid. If NaCl was a pure liquid, that means that we melted those crystals into pure liquid form. Okay, which is different than AQ. AQ means we put it in water and we dissolved it. Okay, so huge difference there. Okay, so again, liquid means pure liquid. Aqueous means it's been dissolved in water. All right, so one of the highlights, like key questions that we always like to put on tests or quizzes is something like, if you have NaClS and you dissolve it in H2O, okay, what will be the results? Okay, it's as simple as knowing that this sodium chloride is being dissolved in water, so you just change that symbol behind it to say AQ. All right, you don't need to figure out how to combine, HNaClO or something like that. It's just NaClAQ. It's dissolved in water. All right, it's easy and beautiful, just like that. All right. That is our notes. Thank you for hanging in there, and we'll see you tomorrow. And if you're tired tomorrow, I'll know why, because you lasted through these notes. All right, thanks. We'll see ya. To our whole. All right, so let's take a look.